In this lesson, lesson 8.1, we're going to learn about a tool that we can use to solve for unknown angles and sides in a non-right angle triangle. Normally in class, I would have us break into three groups, and I would have one group draw a acute triangle, so something where all three angles are less than 90. I would have a second group draw a triangle that has a 90 degrees in it, and then I would have our third group use a triangle where there's an angle in it that's going to be bigger than 90 degrees. And I'd have us all explore some relationships within each of those triangles. What I would have each group do is label their corners A, B, C, and also label their sides using their opposite letter notation. So opposite angle A would be little a, little b, little c, respectively, and so on for all three triangles. But because you probably don't have a protractor at home, I'm going to fast forward a little bit into what the outcome of that discovery would be. And what that discovery would end up being is that regardless of which triangle you have, you would learn through some measurements and some calculations that if you put a little side A divided by the sine of its angle, and it doesn't matter which triangle it's with, and if you were to do a calculation of little b with its sine b value and little c with its sine c value, you would discover that they end up being equal, or end up being the same value in each case, which is a pretty neat relationship. You would also discover that if you've inverted it upside down, if you did the sine of capital A in your triangle divided by its opposite side length, and the sine of angle B divided by its opposite side length, and lastly sine C over its side length, or in other words the inverse of what we see above, you would discover that the answer in each of those three cases also ends up being equal. And this, my friends, is what we call the sine law. Not to be confused with the sine relationship that is in right angle triangles only, which is opposite over hypotenuse. Okay, sine law is the relationship of how these ratios end up being equal to each other. So this is a very powerful tool that we can use to solve, if you will, triangles that are no longer 90 degrees. And it does work for 90-degree triangles too, but our SOHCAHTOA friends are still the simplest ways to solve for angles and side lengths in right angle triangles. All right, so it's very important to recognize when the sine law can be used to, quote, solve a triangle. So there are two scenarios, especially for the ones that are non-right angle. If we have our little acute triangle scenario, for example, and our really big obtuse one, here are the conditions that must be present. We have to know two angles and a side length. So in other words, if I label this ABC, I would have to know the values of two of the angles and a side length, but specifically it would have to be the side length that is either opposite A, or it would have to be the side length that is opposite B. It cannot be the side length opposite C, or the side that is a part of both angles. Okay, that sine law won't enable us to do much with that scenario. Okay, and this is also true for our large triangles too. As long as we know two angles and one of the sides opposite one of those angles, we can use sine law to solve the triangle. The other scenario is that we can know two side lengths. So let's say, for example, we know these two, but then we have to know an angle that is opposite to one of those side lengths. So the third piece of information would either have to be knowing this angle here that's opposite that side, or it would have to be knowing this angle here that's opposite that side. If we know this angle that is between the two sides, sine law does not apply. Okay, so these are the two scenarios by which we can use the sine law. So let's go to it. Let's use a real life example to show how sine law can be used to solve a triangle. So in your notes in example 1, it says solve the triangle. And I will sketch here a rough sketch of the one that you have in front of you. And we have a 40 degree here. We have a side length of 12. It doesn't have any units, and that's fine. We can work with unitless triangles as well, or we could use ones with units. And again, the notion here is solve. So when we see the word solve when it comes to triangles, it means we need a grocery list of things that we don't know about that triangle. So in other words, we're going to try to find these 3 things. We don't know angle A, we don't know angle C, and we don't know little a, side length A. So there's our grocery list. So we can solve for this using sine law because we have present a side length and its opposite angle. That condition must be present in order to use the sine law. And then we can know any other piece of information. It could be a side here, or an angle here or here. But this opposite connection must be true in order for us to solve. So I'm going to suggest that maybe we start by solving angle C. And it doesn't always matter where you start, but the reason I'm choosing C is because we have been given its opposite side length here. What I'm going to do is, if I'm solving for angle C, I'm going to make sure to put it on the top left corner of my sine law ratios. So it will look like this. It'll be sine of C, just like that. And then the sine law says I have to put it in ratio with its opposite side length, which is 12. And I can say that that is equal to, keeping the signs across from each other, the sine of 40 divided by its opposite side length. So again, notice the side lengths have to line up, either both numerator or both denominator, and so do the sine values as well. Now the reason I chose it to set it up this way is because it's going to be easier for me to solve and isolate for C. The first thing I need to do is I need to get rid of dividing by 12. And mathematically we can do that by doing the opposite, which is to multiply by 12. Now remember that whatever I do on the left side, I have to also do on the right side. So what I can do is I can write it like this. I can say 12 times sine 40 all over 14 is equal to the sine of C. Okay, just by putting that 12 in front of it. Now, the only other thing that's preventing me from solving for C is the sine operation. In an earlier lesson, we learned that the inverse sine is the operation that will cancel out sine. So let's take the inverse sine of both sides. And let's remember that when we write inverse sine, it always comes first. Like this. So, in order to find angle C, I need to punch this into my calculator. Now we have 2 types of calculators, you remember. We talked about this in a previous lesson. The one where you can see what you punch in, you can do exactly this. You can enable your inverse sine operation by going shift sine, so that it uses the function that's above the button, not printed on the button. And then we can put all of this inside the brackets. So we can go 12 sine 40. My calculator allows those to happen, and we'll multiply them without putting a time sign. Make sure yours is like that. Now I've closed this set of brackets, but there's still an open set, so I can still do divided by 14, close it, and if I hit equals, I should get the value of angle C. So angle C is 33 degrees. Now it doesn't say in the question how many decimal places to do. If it doesn't say, go to the nearest degree. If it says to the 10th of a degree, then go to a 10th. So since this is a 4, I'm going to leave this as 33 degrees. And now I have found one of the things that I'm asked to in this problem in solving for it. Now just for reference sake, if you don't have a calculator that enables you to see what you're printing, what would the typing in look like? Well, it would be like this. I would do all of this first and then take the inverse sine of it. So I would go 12 times 40 sine, and then I would go divided by 14 equals. Then I would engage the inverse sine operation, pushing second function inverse sine. And you'll notice again you get 33 degrees. Okay. So we've solved for one thing, taken it off the grocery list, done. Let's solve for the next one. Well, I'm thinking to myself, if I now know two angles in a triangle, it's pretty darn easy to find the third one using the fact that all three angles must add up to 180 degrees. Okay. So I should have put a title up here that says Find C, so that you can be clear to me what it is that you're doing in each of the steps of your solution, and it's not just a bunch of random work. Oh, sorry, yep, C. Here we're going to find A. I'll put an angle C in here too. Sorry about that. There we go. All right, so find angle A. So we know that angle A is equal to 180 minus the 40 that we were given in the problem minus the 33 degrees that I calculated here. And when we punch that in, we get 107 degrees. Okay, so this is clearly not drawn to scale, and it doesn't have to be. Okay, in fact, I don't want you to draw to scale diagrams, but I do want you to get a sense of the general givens and what you're trying to find in each scenario too. So that's done. Last, we need to find little a. I'm going to put it down here. And I like labeling things as I go. So I've got 107 up here for this angle. So little a is over here. So again, I can use the sine law because I've got this opposite pairing, and I can create another pairing here between this angle and its side too. Because I want to find a and I want to make rearranging the equation easy, let's let it be at the top of the proportion that we set up. So little a over sine a is equal to little b over sine b. All right, let's put in some numbers. So little b is 14. Angle B is 40. We don't know little a, but we know that angle A is now 107. So we can put that in there, and I'll color code it just so that you know where it comes from. Okay. Now, to solve for little a, we have this divide by 107, sine 107 going on. So if we want to get rid of it, we have to multiply both sides by sine 107. So I can put it in like this here. I can put times sine 107 out here. Those cancel. So little a is equal to 14 sine 107 divided by sine 40. Before we even punch that in, let's get a sense of how big we think that side length might be. We notice that 33 and 40 are roughly the same size. They're off by 7 degrees, but notice that the smallest angle has the smallest side length and the medium angle has a medium length. This angle is quite a bit bigger than the other two. I'm expecting this side length to be quite a bit bigger than 12 and 14 because it's opposite that largest angle, as I said. So let's check our theory and see. 14 sine 107 divided by sine 40, and sure enough, it comes out to 20.8 approximately. So again, if it doesn't state how many sig digs to use in an answer, I want you to make the assumption that we will go with to the nearest degree if it's an angle, and to the nearest tenth if it's a side length. Okay? So, you have now solved the triangle. You found the missing angles, you found the missing side, and you know everything there is to know about this obtuse triangle. I say obtuse because it has an angle larger than 107. This also works for acute triangles. Again, it does work for right angle triangles, but SOHCAHTOA is much faster to solve for right angle triangles than using sine law. So I suggest using it only for non-right angle triangles. Enjoy using your new tool.